In this video, we shall look at a review problem on Biot-Savart law. Let's give a brief introduction. Assume that you have a conductor carrying a current. Assume the direction of the current is like that. We ask, what is the magnetic field produced by this current at that point? Let's call that point P. Let's first divide this entire wire segment into tiny segments like that. The length of this segment is dl. So the length vector is in the same direction as the direction of the current for that element. Now let's assume that the distance between that element and the point of observation is r. The unit vector along that direction is r hat. Biot-Savart law states the contribution to the magnetic field by that element carrying current at that point is given by the following expression. Let's call the magnetic field by that element dB, and Biot-Savart law states dB equals to mu naught over 4 pi I dl, the vector dl, cross into the unit vector r hat over r squared. Mu naught is a constant. It's known as the permeability of vacuum, and it's given by the following number: 4 pi times 10 to the power minus 7 Tesla meter per ampere. That is the SI unit for mu naught. So coming back to the original question, what is the magnetic field created by this entire conductor at that point? That expression can be found by taking the integral or continuous sum of that expression in the box. So by summing up such a current element that covers from this end of the conductor to that end of the conductor, we would be able to find the total magnetic field created by that entire conductor. And it's given by the following expression: mu naught I over 4 pi integral dl cross r hat over r squared. So the Biot-Savart law enables us to calculate magnetic field due to an arbitrary shaped current carrying conductor at a point. Let's get to the problem. A conductor in the shape of a square loop, shown here, edge length is 0.5 meter, carries a current of 12 ampere, as shown in the figure below. So the direction of the current is as follows. Like that. Find the magnitude and direction of the magnetic field at the center of the square. Let's divide up this square loop into sections. So this is section 1, that is section 2, that's section 3, and that is section 4. Let's look at section 1. Let's divide this entire section 1 into tiny elements. One such element is like that. I'm going to take that to coincide with the x-axis and that to the y-axis. The current is going like that. So let's assume the length vector associated with that element is dy. Its position on the y-axis is y, so it's y distance above the origin. The distance between that length element and the point of observation is r. And let's call the unit vector in that direction to be r hat. And let's take that angle to be alpha. So the magnetic field created by that element at the center of that loop is given by Biot-Savart law, mu naught over 4 pi I dy cross r hat over r squared. So the magnetic field created by this entire first segment at the center is given simply by the integral of the above expression, mu naught over 4 pi I integral of dy cross r hat over r squared. We note that that is the direction of dy and that is the direction of r hat. So the angle between them is, this is 90 degrees and that is alpha. So the magnitude of the magnetic field created by this entire segment 1 at the center will simply become mu naught I over 4 pi integral dy. The magnitude of unit vector is 1, so 1 times sine 90 plus alpha over r squared. Sine 90 plus alpha is just cosine alpha, so you can write that there. So let's work out this magnitude of that magnetic field. This r can be related to this y and that distance, which is L over 2, using Pythagoras' theorem. So r squared equals y squared plus L over 2. L is 0.5 meter, so over 2 is 0.25 meter squared. Another thing we need to know, since this is 0.25 meter, y over 0.25 is tangent alpha, or dy is 0.25 secant squared alpha d alpha. So let's substitute all this information inside the integral. So you have mu naught I over 4 pi integral dy is 0.25 secant squared alpha d alpha. Don't forget the cosine alpha, that's that term, over r squared. R squared is y squared plus 0.25 squared. Since a y is 0.25 times tangent of alpha, y squared is 0.25 squared tangent squared alpha. Now substituting inside the integral, you get mu naught I over 4 pi integral of 0.25 secant squared alpha d alpha cosine alpha over y squared is 0.25 squared tangent squared alpha. So combining with this 0.25 squared, you get 1 plus tangent squared alpha. 1 plus tangent squared alpha, it is just secant squared alpha according to trigonometry, so that two terms will cancel. Also 0.25 will cancel one of the 0.25 from the bottom, leaving you with this integral. Now let's look at the limit for alpha. When the tiny element is here, then alpha is that angle. But what is that angle? This is L over 2, that is L over 2, so that means arctangent L over 2 is 45 degrees. It's below the origin, so it's minus 45 degrees, so minus pi over 4. Likewise, when the element is at the top, so the angle alpha here is again plus 45 degrees, plus because now the element is above the origin. So the upper limit for this integral is pi over 4. And now we can find the answer for that integral is mu naught I over 4 pi 1 over 0.25. Integrating cosine alpha with respect to alpha, you get sine alpha, and you need to put the limits pi over 4 and minus pi over 4. Sine pi over 4 is 1 over square root 2. That minus sine minus pi over 4 is minus 1 over square root 2. So that's going to give you 2 over square root 2. We recall mu naught is 4 pi times 10 to the power minus 7 in SI units. The current here is 12 ampere, so times 12 over 4 pi times 0.25 times 2 over square root 2. And the answer is 6.79 times 10 to the power minus 6 Tesla. Note, this is only due to segment 1. Let's work out the direction of this magnetic field B1 due to this segment 1. dy is going up, r hat is going like that. So when you curl your right hand fingers from dy to r hat, your thumb will be pointing into the plane. So the direction of this magnetic field is into the plane. Now we have 3 other sections to do. They all have the same length, meaning L. They are situated symmetrically with respect to the point of observation. So the magnitude of those magnetic fields, B2, B3, and B4, should be the same. Now let's look at the directions. For segment 2, the length vector is going like that in the direction of the current. The r hat presumably can go in that direction. So when you cross from that to that, your thumb will still go into the board. So for segment 2, the direction of current it produces at the center is into the board. What about section 3? The direction of the length vector is like that. R hat is like that. So when you cross from dy to, let's say, r hat, the direction of your thumb will still go into the board. And finally, section 4. The length vector is going that way. Let's say r hat is that way. When you curl your right hand fingers from dy to r hat, the thumb is going into the board as well. So the point is all these B2, B3, and B4 have the same magnitude and the same direction. So they reinforce at the center. So the final answer, B total, is 4 times 6.79 times 10 to the power minus 6 Tesla. The direction is into the board. So the answer is the net magnetic field in the middle or the center of the loop is about 27.2 micro Tesla, and the direction is into the plane. Let's look at the second part of this problem. If the conductor is formed into a single circular turn and carries the same current, what is the value of the magnetic field at the center? So what we have is this configuration with radius r. Now they are made from the original square, so 2 pi r, the circumference of this circle, must be the same as 4 times L. We know L is 0.5 meter, so R is 0.5 times 4, which is 2 over 2 pi, so it's 1 over pi meter. Let's break this circular conductor into tiny elements, such as the one shown, and it carries current like that. The length of that element is dl. The direction of this vector dl is the same as the direction of the current. Let's assume the angular position of that element is theta. So the vector dl is in this direction, and r hat extends radially from the charge element to the point of observation. So that is the unit vector there. The magnetic field created by such an element is given by Biot-Savart law, mu naught over 4 pi r dl cross r hat over r squared. R is the distance between the current element and the point of observation. To determine the contribution of all such elements on that circle, we have to end up integrating this expression, and you get something like that. You see, it doesn't matter where this element is on that circle, the distance between that element to the point of observation is always r. So r is a constant as far as this integral is concerned, and you can take that out of the integral. We note that the integrand dl cross r hat, the magnitude of it, is just dl sine 90, because the angle between this vector and that vector is 90 degrees, so sine 90 is 1. So the magnitude of the magnetic field is given by that, mu naught I over 4 pi r squared. This integral is just the circumference of that circle, and that is given by 2 pi r. This will cancel that, and you're left with 2r in the denominator. So the strength of the magnetic field in the middle is mu naught I over 2r. We know what the value of mu naught is. I is given 12 ampere. This r is given by that, and you get 23.7 microtesla. You can convince yourself for the current going in that direction, and say for a radial direction for the r hat, you curl your fingers from here to there, your thumb will be pointing into the board. So the direction of the magnetic field for this case is also into the board with a slightly smaller magnitude than the first. Thank you for watching.